Behind every successful language model lies one core truth. What you do before training matters more than what you do after. Welcome to Lesson 4, Core Foundations and Practice. This equation captures a core reality of real-world AI. Your clean dataset is always much smaller than your raw dataset. Raw text is noisy, duplicated, or legally unusable. The success of any LLM project begins with aggressively curtailing D into a much smaller high-quality D clean. The tokenizer defines how language becomes numbers. Split too aggressively, and you waste precision context. Split too little, and you'll inflate the vocabulary. The tokenizer determines efficiency and accuracy long before training even begins. There are 3 primary ways to adapt a model. In-context learning, fast, flexible, no training. Fine-tuning, stable and structured. RAG, extendable knowledge without touching weights. The right choice depends entirely on your latency cost and update frequency. To bring those foundations to life, let's compare 2 worlds, the classical trigram model and a modern transformer. We begin by installing NLTK for classical NLP tools and transformers for the GPT-2 model. No GPU required. Everything runs on CPU. We import utilize for tokenization, probability counting, and access to the Reuters news corpus. We download the Reuters news datasets and tokenize those. This is a tiny dataset compared to modern LLM training, perfect for demonstrating the limit of n-grams. We extract the first 300 characters of each Reuters file, just enough to build a demonstration corpus. Then we tokenize and lowercase the text. A trigram model predicts each word using the previous 2 words. Here, we count how often each trigram appears and how often each 2-word context appears. This is the heart of an n-gram model. Given a context, 2 words, we look for all possible next words that have ever followed this context in the corpus. If the context never appears in the data, the model is blind. It cannot continue. Perplexity measures how surprised the model is by the test data. High perplexity means the model can't predict well. Trigram models almost always have high perplexity because they can't generalize beyond what they've seen. Now we compare this classical model to GPT-2, a tiny transformer yet dramatically more powerful. The trigram model can only continue in ways it has explicitly seen. GPT-2 creates fluid, coherent language, even from a simple prompt. And here's the side-by-side comparison. The difference reveals everything Lesson 4 is about. Data matters, tokenization matters, model architecture matters, foundations matter. This small experiment mirrors real-world engineering. Before choosing a model, you must understand your data. Before training, you must choose the right tokenizer. Before adapting, you must choose the right method. To sum up, classical n-gram rely on local statistics. Transformers rely on global context. Data quality defines your ceiling. Tokenization defines your efficiency. And adaptation defines your final performance. In the next lesson, we turn to prompting, the fastest way to steer a model without retraining.